So hello, welcome to the tutorial lecture. This tutorial lecture should give you an introduction onto the hands-on tutorial later on, and some of the concepts will be introduced. It spans a wide range, I would say. We cannot go into every detail, of course, in this time, but we try to something challenging. We try to give you some really interesting ideas which might help us to overcome some of the problems we face in applying reinforcement learning to the real world, and especially to accelerators. And we try to collect some of the main challenges, and hopefully this is helpful. So there are many people involved. This has some history, and things were tested also on real systems. But I come to this in a second. So we will discuss deep meta reinforcement learning and safe shallow model-based reinforcement learning. Two concepts. They are not directly related. And the goal is that you can extend your toolbox. Maybe this gives you good ideas. And this is just a starting point, because in machine learning there is no one-fits-all solution generally, which is expressed, for example, by the no-free lunch theorem. So the more tools you know, the more likely you can address your problem appropriately. These concepts are, I would say, at the boundary of the reinforcement learning things we saw so far. Meta reinforcement learning is a more global concept addressing multiple MTBs, and the model-based approach falls somehow into the domain of control theory as well. Yeah, fresh ideas to attack problems, hopefully. So first of all, I introduce where we will work on. This is the CERN awake steering problem, which might be known to many of you already. Awake is a very interesting experiment at CERN. This is the CERN accelerator complex. It was already shown. And here awake is located. This is how it looks like. So what happens is, this is a proof of principle experiment where you use high energetic protons to create a so-called wake field in a plasma, which gives you high field gradients, which can then be used to accelerate smaller particles to a very high energy in a very short distance. This is not the topic, of course, just the context. What we are interested in is just a part of this experiment where we look at electrons. The secondary particles which are accelerated are electrons. They start here with an electron gun, and then they go through a beam pipe, and then they go into this plasma cell where the rest continues. And we just look at this part and want to solve a very simple but very common problem, namely steering the particles on the right trajectory. This is just a picture of the electron gun where the electron starts. So they start here and they go down this way. These are just the physical details which are not important to us, but what we do is we have a line of consecutive elements. This is a trajectory of our beam, a possible trajectory of a beam, and we can steer this trajectory by changing the strength of dipole magnets along the way, and we can measure the trajectory with beam position monitors along the way. And what you see here is in dashed line a measured trajectory, and in a solid red line a target trajectory. And we want to, so our control problem is to bring the measured trajectory as close as possible to the target trajectory. This problem is interesting for us for a tutorial because, first of all, it was used over many places already in several papers and theses. It's a relatively simple problem. The dynamics is linear. Nevertheless, we have 10 degrees of freedom. It's non-trivial because we put constraints on the actions which are necessary to address the magnets. So you cannot send arbitrarily large currents to the magnets. There exists an analytical solution. So you can find the optimal policy if you don't have any noise or something. And we will have a benchmark policy, which is an optimal policy for a different problem. We can discuss this, but we always compare it to, let's say, a relatively smartly constructed policy, which was done on the paper. The problem itself should be very easy to understand, so we can really focus on reinforcement learning or the methods we apply, and we are not too busy with our MTB. And the most interesting aspect maybe is that the simulation corresponds exactly to a real system, and the parameters were adapted in measurements. So you can then apply these algorithms directly on the machine easily, and this is always a nice feeling when you go from simulation to reality and it works. Yeah. So, okay, all right. This is our MTP. The MTP, the Markov decision process, consists of a state space, action space, reward space, then a transition probability, which in our case is deterministic, but it just says that if you are in a state and you take an action, there's a probabilistic transition to the next state and a reward. And this is stochastic environment in general. Rho 0 is the initial distribution, and usually you have a discount factor, which is set to 1. In our case, we have finite episodes. Yeah, so the state space is then continuous states, the BPMs. The actions are these green correctors, also then and continuous, and both of them are in the interval of -1 and 1. And also the observation is the state. So we say we have a perfect information state. There is no partially observable state involved. The reward is nothing more than proportional to the the root squared sum of the squared distances, and take a negative. So we want to maximize this, but we want to minimize it, of course, in reality. The actions, here you see that it is a linear system, are just taking an action, then you have a so-called response matrix. And this is done in additional way, which means that each time I'm in a state, I take an action and I add up this to this state. We do an episodic training. So the episodes end at one point for sure. And we start an episode with a specific distribution, which was chosen in a way that it's not too easy. Because if you start very close to your target trajectory, of course, there's nothing to do for the agent. So this is a bit put far away. And we terminate an episode if we reach a number of maximal steps of interactions. And we saw this in the last, or in the 2 keynotes, that this is actually a truncation. This is not a classical termination. So this was initially written in gym, that you cannot distinguish, but now in gymnasium, and the tutorial is done in gymnasium, you can separate this. But this is a very high number, so it's not such a problem in my opinion. So it's not fully correctly implemented in one part. In the other part, it's done anyways in the correct way. But this is a point to keep in mind always, how to deal with this. Because you have experiments, you have to end up them in reality, and so you need a number of maximal interactions. The episode ends positively or successfully if we are below a certain threshold, because we are dealing with the real system. We have measurements, and measurements have a measurement uncertainty. So these BPMs cannot measure arbitrary close, they have a precision. And so we say, okay, if the trajectory is measured below a certain threshold, we are happy with the result. Then there's another termination criterion, which is an unsuccessful ending of an episode. This is the case when you hit the beam pipe, because if the trajectory is excurves too large, then you hit the beam pipe, which is I think 20 centimeters in diameter. But Verena, if I say wrong things, correct me, please. Is it 20 centimeters?
20 millimeters.
20 millimeters. All right. Thanks. Yeah, exactly. So it's not important for the tutorial. We have normed it to -1 at 1. And as I said, transitions are deterministic, and gamma is set to 1. And if we speak during the meta part about different MTPs, what we do is we change the response matrix. And the response matrix is dependent on so-called quadrupole magnets, which are not shown here. So they are not visible to us. And if we change this, the response of the system changes. So, okay. General motivation in accelerator physics, mainly. We saw many problems already, so it's really good. We had a good warm-up, and this is not a complete list, just an idea. So mainly the goals are, we want to set performance of our machines. We want to quickly recover performance if something goes wrong, or we want to maintain performance if we have instabilities or so. And maybe we want to quickly adapt our machine to new user requirements, which is more and more often the case to save time and resources. Okay? So I think reinforcement learning is still too rare in accelerator physics and generally in the real world. It's not easy, as we saw, to really use reinforcement learning. And it needs a significant expertise and some computational resources, in my opinion, and really a deep understanding of the problem. And the challenges arise from two sides, namely addressing the problem correctly, but also we have a lot of problems from the reinforcement learning algorithms itself. I call them core RL problems. So first of all, data availability on a real machine is always tricky. Sometimes, many of you know this, we have slow and little data acquisition. Sometimes we might have safety problems, so we cannot do whatever we want. We have not sufficient modeling, and we have poor simulation capabilities. If we fail on a system, it might take a long time to set it back to where we were. Sometimes we have issues with integrating this into system. This gets less and less, but I know some facilities where this is still a tricky thing. Yeah, long-term stability and maintenance of reinforcement learning agents, I think it's not that easy, and general safety and reliability is not given by reinforcement learning by default. Also, we need fast algorithms. Sometimes they have to be really fast, as in the case of the problem we saw yesterday at KD. And yeah, we need computational resources and generalization. Okay, so let's have a look at what problem we face actually. So generally, we have a BOMTP we learned already. So we are in a partially observable system. We cannot have all we want, but we always need to frame it in an MTP to make standard reinforcement learning agents work on it. So this is the first challenge. And then, okay, we start this standard reinforcement learning loop. We have our RL algorithm, which interacts then with the machine. That's so far known. This is challenging already. So first of all, setting up the problem, then choosing the right algorithm, and then the tuning phase comes, which can be tedious and challenging. Everybody knows this, whoever tried to apply reinforcement learning. So the full loop contains even you in the end. You have to adapt your experiments, and this can take very long. And if you want to do really a good job, it needs a lot of expertise. I put this slide back in because we discussed these BOMTPs, and I think this is welcome to BOMTP land. This shows you what the research looks like if you enter this. It's widely scattered, I would say. We have so many approaches from so many fields to address this, and the problem, generally, mathematically speaking, is really hard. So I just quickly go through this to give you an idea, a better idea, and a refresher. So we want to solve this sequential decision problem, which is decision, information, decision, information. Decision is generally stochastic, and we have a feedback system that we can incorporate these uncertainties into this loop that we don't fail too far off. So this is the world. This has a true dynamics, and we just observe parts of it. And from this, we create features, and we have this internal representation. This was discussed by Felix yesterday anyway. And then, based on these features, we design our policy. These features can be the full history or whatever. All right, and this is the full loop you have to address. And this should correspond to an MTP in the end, that you can make it work. Okay, so rarely it's the case that the state is fully informational. Usually you have always measurement and measurement noise, and even this is a BOMTP already. And then you have so many sources of errors. But we want to make BOMTPs MTPs. From a mathematical side, even the simplest feedback system, a static output feedback, is NP hard, where you just have noise on the observation or something. And in general, they are B-space hard. There are many solutions in control theory to overcome this, but this is not an easy thing, I want to say. So go through the slides, ask me afterwards. We don't have sufficient time to discuss this, but I just want to show you that it is tricky, and we have in the end this additional prediction problem before we enter our MTP, which was shown by Felix yesterday. It's a sequence of observations and actions, for example. Okay, you can also, if you have non-stationarity, incorporate the time in several ways. Either for each time step in your problem, you have a specific function, or you add just the time to your MTP, and then the problem gets a bit more complex, but you can handle it. Okay, and generally in most of the libraries, you find this discounted form of the Bellman equations, and this is the easiest form to formulate things. So we usually don't see this part. Okay, this was the first part. We have a problem formulation, we have to capture the right problem. This is the essence. If you don't do this correctly, then you won't solve the correct problem. You should really spend time on this. This is unfortunately not part of this tutorial, but I want to emphasize it strongly, because I saw it very often that people have nice solutions for the wrong questions. Okay, so we also have these other issues which were mentioned yesterday by Antonin, like how to design a reward and all these other things. Yeah. But then now let's come to the core issues of reinforcement learning. We have a lot of problems when we designed this MTP to solve our reinforcement learning challenge. And this is just a list of the most common challenges, which is the sample efficiency was said already, then how stable my algorithm is, if I can train it easily or not, how long does it take to be calculated, how sensitive it is to hyperparameter tuning. Most of the modern algorithms try to give you algorithms which are not so dependent on hyperparameters. Then we have this exploitation dilemma. There is no inherent idea of safety in reinforcement learning. We always try to enforce it via the reward. And also robustness to changes and generalization is a big topic. And we saw this yesterday when Aurélie was asking her question. I think this is something everybody wants to solve somehow in real systems. And then we have this loop. So you decide on a specific set, and then you change something in your problem formulation. The whole thing starts over and over again. So this can be really challenging and time consuming. Let's have a look at the core issues. So I just went through them and we try to mitigate them somehow. Yeah, there's a lot more, but we start with the sample efficiency and we use the awake now as an example. So millions of interactions with a system is only possible in very fast simulations, I would say. And then this goes really down to hundreds of interactions with our system if we use some specific methods. So this is derivative free methods like these black box optimization methods we discussed. So you can work with them, and sometimes this is a good thing to do. And then if you don't have that many data points, usually the next thing is you use fast policy gradient approaches, where they do in each step a gradient step, in each interaction with the system, a gradient step. And the advantage here is that they are really fast and parallelizable. And this can be the way to go. There is an example, A3C, for example. And this brings you a factor of 10 in sample efficiency, a rule of thumb, let's say. Then you go down to batch-based policy gradient methods, where you take batches and do the gradient update, and this makes methods a bit more stable. This is a very well-known algorithm, the trust region policy optimization, which was mentioned several times already. And on the awake, let's say with this method here, different colors mean different tasks, different dynamics. This is done on the simulation. You need around 50,000 steps. And then this is the MPO, which was used by DeepMind in the Tokamak paper. We just had a look at it. This is something in between on policy and off policy. It needs around 5,000 steps, but was really hard to tune. And then we go down to methods which are actor-critic, value-based. Many of them were mentioned also by Antonin. It's classical Q-learning, DDBG, DD3, soft actor-critic or normalized advantage function. You go down again by a factor of 10. Here's an example. The soft actor-critic needs around 500 iterations on our program. Then this was mentioned by Felix yesterday, fortunately, and I learned a bit after discussing with him in the evening about this algorithm. So it promises things it cannot hold, but nevertheless, I say what it promises here. It's a model-based method. You develop a model of your system dynamics using an ensemble of neural Bayesian networks, and then you apply a model-free method, which just interacts with this model you learn from data as it would be the real system. And this is done in a way where you have short rollouts and some tricks, and then you get this monotonic characteristics. This goes down to around 100 already, but there's a lot of algorithms out there, and then we have model-based shallow methods. We see in the tutorial, here's an example of the GP-MPC, and shallow means we don't use deep neural networks. In this case, we use Gaussian processes. So this looks good. Why not taking just this one? Because it's the most sample efficient. Yeah, this is not a full story, of course. Yeah. So if we say we start here, here it's interesting. We say we need thousands of iterations, or we go down even. The price always is, if you go down, some other things decrease. Unwanted things like hyperparameter tuning gets more complicated. You get higher computational burden. You get a lot of bias in many ways. Yeah, so as soon as you use temporal difference learning or Q-learning, then you introduce a bias, and this says, okay, if I go up, I win in stability. I get maybe some guarantees, although I have to use more samples to train my system. So this is why you don't use just the most sample efficient one. It's always a trade-off. Yeah, and it would be nice to have an algorithm with the guarantees from here and put it to here, for example, as we see in a second. Maybe this is somehow possible. This is just an idea. This is incomplete. We can discuss this, but I think this was shown in the talks yesterday very often, that how can we apply reinforcement learning? In the exceptional case, we have sufficient data, we can train our agent directly on the system, and then we get the policy we want. But this is an exception. Usually there is a simulation in between, in some form, whatever, and then if it is a really good simulation, okay, we can go directly and apply it to the real machine. Usually what we do is we have the simulation, we train our model-free agent on the simulation, try to find a very good setting, and then maybe apply it in this way. So this is how you could use the simulation. But if you cannot do this, what you do or what you try is to adapt it to the real world, to minimize this sim to real gap somehow, and then apply it. And we will concentrate on this part. And also there's another way. You use these model-based methods, which are very sample efficient, again directly on a machine, but reinforcement learning is done indirectly, and then maybe you can solve your problem. Okay, so simulation based is the first thing, and this is not easy always, as many of you know. There are many attempts how to address this, and we will address this using meta reinforcement learning. Then the other way is this model-based approach, and we don't have any simulation in this case. So what is the best and fastest way in this case? And usually on one day we train an agent, but the next day or the next week it doesn't work anymore. So it should be able to adapt very quickly if you retrain it. That's the motivation. Yeah. So part one will be meta learning, and I hope you have many questions because we go very fast through this. But these are the key points. So we have a simulation. We know the simulation is not totally accurate. We want to adapt. We wanted to prepare our agent to be able to adapt to reality as fast as possible, and also in a very nice way. As we see, this is sometimes possible. And the second part is the model-based reinforcement learning, where we use DirectRL with our system and use, as we do a model, we can use concepts from control theory, and this gives us some cool properties as well. And we leverage these cool concepts from there. And I would call it, this is the Bayesian optimization of reinforcement learning we see today. We saw so many BO talks and BO examples, so extend this idea to reinforcement learning now. This is extremely sample efficient. Okay, meta-rel. So we have some source domain, and we want to get into a position where we can solve a problem more quickly in a target domain, in a new downstream task. Yeah, and usually this is done with transfer learning, and you try to incorporate your prior knowledge somehow into your system, that afterwards it learns faster or even in zero shot. So you do reinforcement learning on the simulation, and then you try to adapt it to your real problem, and you have your policy. There's something where you vary this simulation. So you have several simulations. This is also, for example, domain randomization or multitask learning, which is very closely related to meta learning. Then you try to have a policy which is able to adapt quickly on several scenarios which might appear in reality, and then you have your policy. These approaches work sometimes and are really nice, but they have some shortcomings, because meta learning is aware of the second process, while transfer learning and multitask learning usually is not. So we do our training in a way which is aware of that there will be a new task and I have to adapt to this task quickly. This is the separation of these worlds, I would say. Yeah, so the knowledge acquired from learning many different tasks can be leveraged to expedite and improve the learning process to new tasks. This question mark, but this is already the goal. So how do we do this? We have a set of different tasks, like we want to walk, we want to ski, we want to learn how to ride, how to stand, how to ride a bicycle. So the agent sees these different tasks and learns to learn on this task. So it learns really to learn everything as fast as possible, with the hope that then finally, if we have a new task, the full knowledge applies to this new task, and we just have to learn what is there to learn to satisfy the new conditions. Yeah, so it's learn to learn. This is the important part. It's a bit confusing at the beginning because we deal with several MTPs soon. Yeah, so there are many ways how you could incorporate this idea. We just focus on gradient-based meta learning, and it gives us the possibility to really quickly adapt to our new task while being aware that we want to do so. So we have a distribution of MTPs. Sorry. This distribution of MTPs is our training environment. So it's not a single MTP, it's really a set of MTPs. And then we just sample out of these specific tasks. So we use the model agnostic meta learning, which is not very new. It was introduced in 2017 by Chelsea Finn and Sergey Levine and colleagues. But it's a super interesting algorithm because it's universally applicable to differentiable problems. So it's not only specific to what we are doing here. So you can transfer this idea. It should give you just the idea, and you can apply it in many scenarios. Yeah, it requires gradients to the second order, which can be a bit tedious, and there are workarounds to circumvent this. But generally, if you can do automatic differentiation, this works. Okay, so this is how the process looks like. Don't expect to understand this immediately. This is a bit tricky, and I just show it that you see how it works, and we have time to discuss this during the tutorial. I would say mainly just look at this picture here. What we want to do is we are looking for a meta policy, which is parameterized by theta, which sits in the best spot, at the best spot in a parameter space, in order to achieve every task out of a distribution on the fastest way. So this means along the training, we come to better and better positions, and it's done via the gradient. So it measures the gradient steps for each task and tries to find the best spot in this parameter space to reach the tasks as fast as possible. And this has many advantages. This can generate a very robust policy under circumstances. Okay? Are there any questions yet on this? So we just move on and have a look, and we can discuss this slide later on. So our setup uses trust region policy optimization for the meta optimization part. And then further on, when we adapt our policy to a concrete example, we use a policy gradient with this general advantage estimation, which was mentioned, I think, by Antonin yesterday already. It's a fast and stable reinforcement learning. So there are scenarios how you could apply this. So you have your simulation with uncertainties in it. So it's like a bomb TP. You meta train it with the manual method, and then you hope that you can, if you are on the real world, apply it in a few shot learning scenario. And in the end, you get a policy in form of an artificial neural network, which is relatively fast to compute. Possible scenarios. Please, if you have any further ideas, tell me. Usually we have an inaccurate simulation, and we want to prepare the agent in a best way that it learns reliable and fast than on the real task. We could have non-stationarity, so we know that the system drifts. We cannot predict this, so we could use this concept to have an agent which quickly then can be retrained when the system has changed. Or you can also save some computational resources if your simulation is very time-consuming, and so on. These are now experiments. So this is our setup during the tutorial. We have our awake, and in the background, we vary the quadrupole settings, which then change the dynamics of the system. It's a linear dynamics, but the response metrics change. So we use this distribution, which is generated by, we have the real system, the measured awake system, or the design optics, and we put a uniformly distributed range, I think up to 20% or 25% of the settings. We assume we don't know them, okay? We have a simulation, we don't know these settings in advance, but we know the range is more or less, and we want to prepare our agent to perform well on this. So this is an example for response matrices, how they look like. This is a lower triangular matrix because along the line, the causality says that if I change the first element, this impacts all other elements, of course, but if I change the last one, it doesn't apply to the previous ones. These are verification or test tasks to evaluate our performance then in the end. We fix them that we can do good metrics. Okay? And then we do the meta training. This is an example how it looks like. I cannot go too much into details, but this is how the learning curve looks like. And of course, since we are training a meta policy, it's not the best performance on each task. This is averaged over these 6 tasks here in this plot, because it sits at the spot where it adapts then quickly to your new task. Okay, and then this is the outcome of our experiment. There are 3 scenarios shown, averaged over several tasks, again over these 6 tasks. And this is the learning curve in batches. Yeah, so we do a batch training which consists of finished episodes each time. And if we just randomly start with our policy gradient and we do the standard reinforcement learning training, we see this is a noisy start somewhere and then takes some time. I mean, it goes very nicely up and then it converges to somewhere. If you would say, okay, I take just the center of this distribution, I train my agent on the center of these MTBs and then try to fine tune it or adapt it to my system, then I'm here somewhere. We also have some noise, but this is what is generally done. And the hope is that meta reinforcement learning gives you the possibility to really prepare your agent that it stably and fastly learns when you apply it on your system. As we see here, this is the upper plot. So it looks very promising, right? Okay. Yes, sorry. I should not have added these slides yesterday night, but it's okay. So quickly, what does this say? We use an fast on policy algorithm. We incorporate our prior knowledge in a clever way, and then we end up in a place where we can transfer all these nice properties to a place where we can really apply it then to real systems. So it's a stable training then afterwards. It's not only fast, it's also brings some other nice properties. Okay, this was demonstrated more than 1 year ago on the Awake. So we just tried it. We can discuss if this makes sense or not, but it's always nice to run it on a real system, and it worked. Okay, part 2. I quickly go through it. It's another concept. So it's a very cool concept, but it's also just a small part of the tutorial, although it's a very promising avenue, and I didn't want to skip it because now is the time to go and we should just move on. So or can we have a fast reinforcement learning with guarantees? Is this a dream? Let's start with if we would have a perfect model of our problem, or a very good model, then we would go and use optimal control theory. And I'll show you quickly what this means. So we generally in control theory have 3 main ingredients with mathematical description of our system which has to be controlled. These are called state space models. We use MTBs. All of you are more or less familiar now with MTBs. Usually we have a criterion we want to satisfy, we want to optimize to, which is the cost function, which we have to specify, which in our case is the reward, and we have to design this reward according to some criteria, which is not only what we want to achieve, but also how we want to achieve it. And we see some nice features out of control theory, which give us some more control, as we discussed before already with this action limit optimization. So, okay. And then we also can specify constraints, control or state constraints. This is not easily possible with reinforcement learning. In our case, the model assumptions are like this. We have stochastic dynamics with the Markov property and a specific form of uncertainty. In our case, it's just a Gaussian noise. And in stochastic settings, of course, we optimize not for a single value, but for an expectation value. Okay? First solution to address this is dynamic programming. This is the world of reinforcement learning generally, or of Q learning. So we want to reach this point. There is this principle of optimality, which is a sufficient condition. So it says that if you have a Markov property, you can start from the latest step to your target, find the optimal policy, and then from there on you move backwards, you again find the optimal action for this and go back and so on. This is this backwards recursion, and it gives us in the end a closed loop solution. So for every state in our system, we know how to interact. And of course, these are the classical algorithms which use this. They were already shown in the crash course quickly yesterday, but there's no direct notion for constraints in states or actions. Yeah, and in control theory, usually you have a non-feedback control. So you use calculus of variations. You can really calculate the full trajectory. There's a very famous theorem by Bontriagin, which is the Bontriagin's maximum principle, which is only a necessary condition. But you want to go from A to B. You just vary the path until you have the best solution. And how to find this solution is said by this theorem, because it turns your variation problem into a minimization problem at each point in the sequence. Yeah, and then you find this optimal path. So it's a bit different to dynamic programming. And the good thing here is that it can handle constraints. We can really plan the full trajectory in all details and give it whatever criteria we want to meet. But it's an open loop. So I plan in the future, and if something happens on the way, this approach is not aware of the change. So we can never stabilize the system unless we have the perfect model of everything. And the question is, can we have the best of both worlds? And the answer is yes, somehow. Namely, we use this open loop controller we just saw with dynamic programming in a direct way. This just says, is the state the observation or not? And we use this Bontriagin's, or other way around, sorry, Bontriagin's principle here and dynamic programming on the other side, which here is the closed loop and the open loop. And then in the middle, there sits something which is called a model predictive control. Okay, so it somehow tries to merge both properties, and this is just the key idea. We want to optimize this infinite optimization, infinite horizon optimization problem. This is just the mathematical formulation. And what we do, we truncate it, which means we just plan for a specific length in the future, and the rest is then estimated via a value function, for example. And then we just solve this optimization problem, because this we cannot solve it easily, and this is how it looks like. And this we will see in the tutorial. So we sit in a specific point in time. We already observed something, and there's a future to come. This is a reference trajectory we want to meet. This happened, this comes, and this is the measured output. And along the way, we already applied some control. Okay? And then what we do, we predict an output with a specific prediction horizon, which uses the model we have at hand, or we will learn from data in this discrete number of steps. And okay, this would be now the open loop control. But to be robust against some perturbations, we don't do the full trajectory, we just take the first action and the whole thing starts over again, and we optimize again. This is all what MPC does, and it's a really clever idea. But we don't have a model in reinforcement learning, so we learn the model, we have to learn it from data, and then do this idea here on our model before we apply again the actions to the real system. And now quickly, I show you the GP-MPC idea. Yeah. So what we do is we have a data-driven model. We use this MPC idea I just showed you. We optimize. We take this action, apply it to the system, and again retrain our model to get a more accurate model. Because the closer the model is, the better the planning is, the more stable this whole thing gets. And these are the steps. You set up the dynamics reward model, which in our case is done via Gaussian processes. We use this Born-Triagon's maximum principle to optimize this problem. In our case, we can use the gradient information because we do it in a really clever way here. We optimize this. We can consider here safety, and then we just do the training. And then in the end, this is important, you don't get a policy as an ANN before. We get a model in form of a GP where we always optimize then again if we apply it. This is a price we have to pay. And of course, there are ways out because this is very time consuming because this is a non-parametric approach to functional approximation, which doesn't scale well with big data, but there are so many tricks and we have so many GP experts here. So ask them how to overcome limitations or to apply some tricks here. I don't discuss them. I also skip this. So we discussed this aleatoric and epistemic uncertainty yesterday a bit. And yeah, Gaussian processes are really nice to be short. The important thing is only that this is only possible, so you can only apply Born-Triagon's maximum principle if you have deterministic dynamics to plan this trajectory ahead. And here the trick is that we use the mean and the covariance as fixed parameters which we propagate through our system. Yeah, and then in this way you can set up that you can propagate this, including the uncertainty. Okay. I go quickly through this. These are just details from the algorithm. We can discuss this later on. These are the tests on the machine. This was really cool. So in November 2022, we applied this to Awake. And when we turned it on, so here what you see is a plot you will see over and over again in the tutorial, the length of the episode before its success is successfully or unsuccessfully. This is the final reward here in green. And this is just a visualization during the experiment to see somehow what happens. This is the trajectory in Awake. So let's say the relative trajectory to the target trajectory. And here you see dotted blue the previous trajectory, and then almost at zero already, which is the target, the final trajectory. And this only took, so we of course prepared it on a simulation a bit, but this only took a few steps to solve this 10 degree of freedom problem. And we were really impressed. We were not sure if this is real, and we applied it again. It worked again. So this was really something cool. And also we saw it stabilizes the system. Okay, this is the result of all these experiments we did. So you see that it needs just a few steps to adapt, and then it solves the problem. This is initial position, this is final position here, this is number of steps here, and this is the number of cumulative steps, which is here around 20, between 20 and 30. You can also incorporate safety. We have a model, and this is the cool thing about this. And unfortunately, Felix is not here anymore. He's the expert on safe exploration. But since we somehow have an idea about the world through our model, we can of course safely explore the world. And what you see here is we have safety constraints that if we hit the wall at 1 or -1, then the episode stops. And here you see the states, and you will see this graph in the tutorial anyways. This should go to 0. So what happens here is that if you get close to the boundary, it starts to behave very smoothly, to understand the world better, and as soon as it does, it optimizes the problem. Also here on the other side, it does this and it solves the problem. So it doesn't violate safety constraints that often, which is not easy by using reinforcement learning. And this is done on the real system. So this was direct reinforcement learning training. Yeah, so if you then don't have safety, this just indicates out of 5 trials, how often do I hit the wall here in green. And if you consider safety, it doesn't hit the wall at all, for example, in this case. But also you could incorporate non-stationarity, which is always a topic. And this is just a trick you can do. So what is done here is this very closely related to the variation of the quadrupoles. So we just, I show here, just vary the quadrupoles with a very small, very long time scale perturbation up to 25%. And we just incorporate the time into the GP model, which means that it has a look closer to more, puts more weight on more recent data than data which is far away. So it's super easy conceptual, but it turns out to work very well. So here again, this is the failure rate, and this goes down. So this is something you should have a look at. Okay, wrap up. We saw the meta reinforcement learning, the MAML, the model agnostic meta learning. We see that it leads to rapid and stable adaptation. The generalization is maybe relatively good. It's a very simple and elegant concept, which can be also applied to Bayesian optimization, for example. In the end, we get very fast computing algorithms as a policy out there, so which is also a nice feature to have. In the best case, we also see a monotonic improvement, which might be important if you want to apply it to a running system. You want to do it in a non-destructive way. You won't lose the full performance. Of course, you need some idea about the world. It should be somehow a convex hull of all the uncertainties in your simulation distribution of MTPs. Yeah. Also, it's computationally intense. So we don't run the meta training during the tutorial. You can run it. It takes about 30 minutes, I think. At the moment, we prepared the weights for you, but you can try it out and report if it doesn't work. The implementation is a bit tricky. So it was a way to go there, to be honest, just that you know. And also the tuning is not that straightforward. It's a very complex approach already. These are the drawbacks. The key points of the GP-MPC you will learn. I showed you here. In the end, you get this GP model out. It's extremely sample efficient. It can handle some limitations, some constraints. It doesn't scale well. I mean, we have a 10 degrees of freedom system, which means we have 20 inputs and 10 outputs, which is relatively high dimensional, I would say, but nevertheless, also it the computation time increases with the amount of data. You always have to run the optimization when you apply this algorithm to the real system, which can be time consuming. So the further you plan your horizon, the more the optimization has to do. Implementation also can be tricky, but in the tutorial you get a good template, I would say. Tuning might be tricky, and I didn't say any details. We will do this in a tutorial. Summary, machine learning is always a trade-off between several criteria, in my opinion. Yeah, the more tools, the better. So real-world applications and accelerated domain has some unique characteristic, and this narrows down this toolbox. Yeah? And reinforcement learning, or the implementation of working reinforcement learning, is a challenging task still. So I hope this inspires you, these two methods we show inspire you to overcome some of these limitations. Is there a question? Yes.
For the meta learning,
yeah.
I have different questions. So you use TRQ for the outer loop or for the inner loop?
For the outer loop.
And for inner loop? Could you use anything?
Well, it should be differentiable. So in this case, it's a policy gradient because it's an easy way to go. But exactly, so you could think of what could I use in an inner loop as an alternative. Here, the policy gradient is a very nice method if you sit at the right spot in space. So this is really a good way to go generally, but this can be extended and you can think of using also a DRPO inside or something else to get these guarantees or whatever is available, right? It's just that you prepare the metabolis in a way which is then adaptable quickly and you see what properties you need in the end, I would say.
But the inner loop is not the MPC now.
No, sorry. These are two separate concepts.
Okay, good.
We have time during the tutorial. It was a lot of material. I'm sorry. Go through the slides. They are online and ask. I tried my best.
There's time during the tutorial also for questions. There's a lot of time.
Yes. So I think we have a lot of fun in the afternoon in applying these methods and understanding them better. Here's a list of references. So I really have here 3 reinforcement learning or meta learning courses I recommend. They're online. This is the deep multitasking meta learning by Chelsea Finn. She's at Berkeley and she does a great job. She's at Stanford. Sorry? Yeah, my fault.
She was at Berkeley. She's not.
Ah, okay. Thanks. Yeah, then we have Sergey Levine. He's one of the superstars also in deep reinforcement learning. All his lectures are online and are always updated. So very recent things and some ideas you saw, I more or less implicitly copied from him. And then there is Emma Brunskill. She's at Stanford. Very good. She does also a great job. And I use Emma's lecture as a template for my own deep reinforcement learning lecture. Here is a list of papers. Here's the GPMPC and the MAMO and so on. Here's a list of very good books. The first 2 are reinforcement learning. The second 2 are probabilistic machine learning. Very good state-of-the-art books, very concise, very thick, 1,000 pages each by Murphy. But they are freely available and they're a really good resource if you want to look something up for the first time. And also Murphy discusses the GPMPC, for example. Then there are books on standard books on control theory, and yeah, you just have a look. Only the last one is hard to find, but you can find it online. It's just not freely available. And there are other resources, for example, the course from last year's workshop, and yeah, just a book about convex optimization. So thanks a lot. And yeah, let's have fun. And now we go for lunch. And you ask me during lunch.